We're doing an experiment with Newton's law of cooling. What we're going to be doing here is, let's suppose that we couldn't drink our coffee for 5 minutes. Should we add the cream first, or should we add the cream at the end? Newton's law of cooling explains which is better, and I'll explain why when we're done with the experiment. So let's get started. We're going to put equal parts of coffee into each of these 2 coffee cups, and we're going to measure their temperature over the course of the next 5 minutes and determine in which case the coffee stays warmer. Add the cream to 1, and let's start our experiment. Here we go. I'm going to stir the coffee just to make sure it's all the same temperature. While the experiment is running, we're going to go and cut the strawberry pie so that we can have dessert with our coffee. We'll be back in 5 minutes. So we've got the pie all cut. It's almost time to run our experiment. We just have to wait for our 300 seconds, and then we will dump the cream in, and then we'll eat our pie. Well, we've got 294 seconds. When we get to 300, it's time to pop. And here we go. So we add the cream, and if you notice, the temperature adding the cream later is slightly lower, just slightly lower than the temperature that it would have been had we added first. Here's the explanation. Newton's law of cooling states that the temperature gradually returns to the equilibrium temperature. If you notice on the graph, it shows that the temperature, the ambient temperature here in the room, is about 17 Celsius, about 58, 63 Fahrenheit. A little chilly, but that's why we've got a sweater on. I think it's now time for us to have our pie. I'm going to stop the experiment and eat the pie. Now, turns out my wife doesn't want her piece of pie, so you know what that means. More pie for me. Very tasty. And delicious. That's Newton's law of cooling in action. It's time to analyze the temperature of the coffee experiment. If you notice, the red represents the coffee that did not have the cream added to it. The blue represents the coffee that did have the cream added, and then the green way down at the bottom represents the coffee that represents the air temperature. What I'd like you to pay attention to is the exponential equation. Now, this program does a little bit different method of doing the exponential equation. For this first one, it records the exponential equation as 21.78 e to the negative 0.001753 t, and then it adds a constant term, which in this case is 39.08. So what it's saying is that the temperature at the beginning, since E at the beginning would be 1, so you'd take 21.78 times 1 and add 39.08, and you would get this temperature here of about 61 degrees. For the second equation, for the lower graph, the equation says 24.01 e to the negative 0.001339 t, and then this one is plus 33.87. The only thing that we really want to pay attention to is the size of the constant term here in front of the t. If you notice, in the first case, the temperature decreases about 0.17% per second. In the second case, it decreases only 0.13% per second. And the reason for both of those is that Newton's law of cooling is related to the difference between room temperature and the temperature that the item is at. And since the already cooled coffee is closer to room temperature, it won't cool as rapidly. The coffee that is higher will cool more rapidly. Practical applications to this principle are found also in heating a house. It's easier to heat a house to a cooler temperature compared to outside than to a warmer temperature compared to outside. In other words, the bigger the temperature difference, the more expensive it is to heat your house. That's Newton's law of cooling in action.